Dear students, under the lecture series on the topic complex analysis, in our previous video lectures we learnt about limits under complex analysis. Now here we are going to learn about the continuity of a complex function where it is defined as the function f of z is continuous at a point z0 if it satisfies these three conditions. The first condition says that limit z tends to z0 of f of z exists. That is, the limit of the function f of z exists as z tends to z0. The second condition is f of z0 exists. That is, the function exists at the point z0. And putting these together and equating them, we get the third condition. That is, limit z tends to z0 of f of z will be equal to the value of f of z0. That is, we know that the limit exists, and in particular, the value of the limit will be equal to f of z0. So, if a function f of z satisfies these three conditions, then we say that the function f of z is continuous at the point z0. Now let us see a problem under this topic. The first problem is to show that the function f of z equal to real part of z squared by mod z for z not equal to 0 and 0 if z is equal to 0 is continuous at the point z equal to 0. So as the first step, we have to show that the limit of this function exists. Now in order to show that the limit exists, from our previous video lecture, we have learned that in order to show that the limit of a function exists, we have to show that the limit is unique along any different paths that we consider. So let us first prove that the limit of this function exists. So first we shall write the given function f of z, which is equal to real part of z square divided by modulus of z. Now we know that the complex variable z is equals to x plus iy, and we have to take z square. So z square will be equal to x plus iy the whole square, which is equal to, expanding by using a plus b the whole square formula, we will get x square plus 2xiy and then plus I square y square, and that is equal to x square plus I multiplied with 2xy plus minus, because I square is equal to minus 1, so minus y square. Gathering the real part and separating the imaginary part, we get x square minus y square, which is independent of I, are the real parts. I multiplied with 2xy is the imaginary part. That is, 2xy is the imaginary part. So this is the real part and this is the imaginary part. Now here we have to consider real part of z square. So this will be equal to, what is real part of z square? It is x square minus y square. So x square minus y square divided by, we know that modulus of z square, by the formula we know that it is equal to square root of x square plus y square. So here we will be having square root of x square plus y square. So this is our f of z. Now we have to first prove the first condition, that is the limit exists for this function is what we have to prove. Now here if you see, we are going to prove that it is continuous at the point z equal to 0, which means that the point z0 is equal to 0. So in order to prove at this point, so here z0 will be equal to 0. So therefore we have to consider limit z tends to z0, which is z tends to z0 is what? 0. So z tends to 0 and f of z we have to take, that is x square minus y square by square root of x square plus y square. Now we know that z is a complex variable x plus iy. So if z tends to 0, it implies that x tends to 0 and y tends to 0, because if z tends to 0, the value of x and y will tend to 0. So applying that over here, this will be further equal to limit x tends to 0, y tends to 0. We have to write in this way because we have the function in terms of x and y. So x square minus y square divided by square root of x square plus y square. Now further, we have to now check along one of the path. So we shall consider the path along. So we shall consider the path along y is equal to mx. So we are going to consider the path along y equal to mx. So if we consider that path, this limit will be equal to limit x tends to 0 alone we will have, because we have taken y is in terms of x itself. So y is equal to mx. So we shall, wherever we have y, we shall replace it by mx. So this will be equal to x square minus, now y is mx, so m square x square divided by square root of x square plus m square x square. Now in the numerator, if you see, x square is in common, so we will be having 1 minus m square. And in the denominator, within the square root, we have x square common. So square root of x square multiplied with 1 plus m square. Now taking this x square out of the square root, we will be getting, in the numerator we have x square multiplied with 1 minus m square divided by, so when we take this x square out of the square root, it becomes x, and then square root of 1 plus m square. Now if you see, one of the x gets cancelled. So it will be x multiplied with, so this will be equal to limit, here also we have to write limit x tends to 0, here too. And then limit x tends to 0 of x multiplied with 1 minus m square divided by square root of 1 plus m square. So when we put x is equal to 0, because we know that x tends to 0, and we have the variable x over here. So when we put x as 0, we get this full limit to be equal to 0. So therefore we have proved that the limit of the function f of z exists, and it is equal to 0 in fact. So we have proved the first condition, that the limit exists. And this limit will be definitely unique, because this is one of the path y equal to mx. If you choose the path x is equals to my also, you will get the same. If you choose any other path also, finally the limit will be equal to 0. If you want, you can check it out. But I have shown for a general path y equal to mx. Therefore the limit has turned out to be 0, and therefore the limit exists. So therefore I have written that limit z tends to z0 f of z exists. So first condition is done. Now the second condition is we have to show that f of z0 exists. Now what is the function? That is, here we have f of z is this. Now f of z0 means at the place of z we have to put 0, because z0 is what? 0. So when we put 0, what is f of 0? We know that when z is 0, it is equal to 0. So therefore f of z0 also exists. So remember, in the question z0 is given as 0. So when we put f of z as f of z0, that is f of 0, we know that when z is 0, it is equal to 0. Therefore f of z0 exists. So that is what the second thing is. So we have proved that f of z0 exists. So this is also done. Since we know that f of z is equal to 0 for z equal to 0, and we know that z0 is equal to 0. That is what. Now third condition is to prove that limit z tends to z0 of f of z is equal to f of z0. Now what is limit? So we will write that limit z tends to z0 of f of z, which is equal to what? Limit z tends to, because z0 is 0, z tends to 0 of f of z. Just now we have found that the limit f of z is equal to what? It is 0. We found here. So limit z tends to 0 of f of z is equal to 0. So therefore this is equal to 0. Now we have to prove that by definition we have to prove that limit z tends to z naught of f of z is equal to f of z naught. So what is f of z naught actually? F of z naught is equal to f of 0 because z naught is 0. But what is f of 0? It is equal to 0 only because f of 0, that is when z is 0, this is equal to 0 only. So third condition is also proved. So hence we have shown that all these three condition is proved for the given function f of z equal to real part of z square by modulus of z. So therefore this function, given function, is continuous at the point z equal to 0. Hence we have shown that f of z is continuous at the point z equal to 0. We shall see a similar problem now. Now here we have the next problem where we have to show that the given function is continuous at the point z equal to 0. Now we shall first take and write the function. What is the function? F of z equal to imaginary part of z square divided by modulus of z, which is equal to, what is imaginary part of z square? In our previous problem we have seen what is z square. It is x squared minus y square plus I multiplied with 2xy, where x square minus y square was the real part and 2xy was the imaginary part. So for z square, the imaginary part is 2xy. So we should take and write that. The imaginary part of z square is 2xy divided by, what is modulus z? It is square root of x square plus y square. So we have found what is f of z. Now in order to prove that the given function f of z is continuous at the point z equal to 0, we need to prove the three conditions, that is limit z tends to z naught of f of z exist and f of z naught exist, and this limit will be equal to f of z naught in particular. So first we shall prove that the limit of the function f of z exists if z tends to z naught. Now we have to consider limit z tends to z naught. What is z naught over here? Z naught, the value of z naught is at the point where we have to find. We have to prove that it is continuous. So that is given as 0. The point z naught is equal to 0. So limit z tends to 0 of 2xy divided by square root of x square plus y square. Now since the function is in terms of x and y, we have to change the limit also in terms of x and y. And since z tends to 0 and we know that z is equal to x plus iy, the value of x will tend to 0, y will also tend to 0, and we will have 2xy divided by square root of x square plus y square. Now in order to prove that the limit exists, we have to prove that the limit is unique along different paths. So we shall consider a path. So what is the path that we are going to consider? Y is equals to mx. So this path we shall consider. So if we consider that, so this will be equal to limit. Now since we have changed y in terms of x, it is enough if we have only the limit for x. And 2x multiplied with what is y? Mx divided by square root of x square plus m square, okay, x square, because y square we have here, y is mx, so m square y square, so that's equal to 2m x square we have in the numerator when it gets multiplied, divided by square root of x square is in common and we have 1 plus m square. Taking this x square out of the square root, we have 2m x square divided by x square root of 1 plus m square. So one of the x gets cancelled and we are left out with 2mx divided by square root of 1 plus m square. Everywhere we have to write limit x tends to 0 without fail. So limit x tends to 0 and limit x tends to 0 over here also. Now when x tends to 0, what will happen to the numerator? When we substitute x as 0, this fully becomes 0. Therefore, limit x tends to 0 of this function, that is 2mx divided by square root of 1 plus m square. When we substitute x as 0, it's equal to 0. Therefore, the limit of the function exists and it is equal to 0. The first condition is satisfied. So therefore, limit z tends to z naught of f of z exists. Next we have to show that f of z naught exists. So This is already given in the question. Since z0 is 0, we can see that f of 0, that is when z takes the value 0, it is equal to 0 only. So if it is equal to 0, it means that f of z0 exists. Also, since the limit which we proved that it exists is equal to 0 and that is equal to f of z0, we have proved that limit z tends to z0 of f of z is equal to f of z0. Therefore, we have proved the third condition also. First, second and third, all the three conditions are proved. Therefore, the function f of z given in the question is continuous at the point z equal to 0. Hence, we have shown. We will see one more problem where we will show that a function is not continuous. Now here we have the third problem which says that prove that the function f of z equal to real part of z by z for z not equal to 0 and 0 if z is equal to 0 is not continuous at the origin. So origin means what? Origin is at the point when z naught is equal to 0. So when at this point, that is z is equal to 0 also you can say. So at that point we have to prove that the given function f of z is not continuous. Okay. In order to prove that it is not continuous, by the definition of continuity, we know that a function is said to be continuous if it satisfies all the three conditions. So all the three conditions should be satisfied. Now in order to prove that it is not continuous, it is enough to prove that any one of the condition is not satisfied. So we shall prove that prove the first condition, that is, first condition is we have to say that the limit of the function f of z exists. So let us see whether the first condition is satisfied or not. We shall try to prove that first condition itself is not satisfied. That is, the limit does not exist. If we prove that the limit does not exist, it will imply that it is not a continuous function. So let us try to prove that. Now here, in order to prove that the limit does not exist, from our previous video lecture we know that we will take different paths and we will try to prove that the limit is not unique. So in order to prove that, first we shall consider the given function f of z. So what is f of z? It is equal to real part of z divided by z. So what is real part of z? We know that z is equal to x plus iy. So the real part of z is x. So x divided by, now z is x plus iy. Now we shall consider this. Now we will take the limit. So limit z tends to z naught. So what is z naught? It is at the origin. So z tends to 0 of f of z. So that is equal to limit, and since z is equal to the x and x plus iy, we know that z tends to 0 implies that x tends to 0 and y tends to 0. So we have to rewrite it as x tends to 0 and y tends to 0, x by x plus iy. Now we have to choose a path. So let us choose along the path y is equal to mx. So along this path, so since y is equated to mx, we will have the limit as limit only for x tends to 0, because we are going to replace y in terms of x. So x divided by x plus y is what? Mx. So it will be mx. So that's equal to limit x tends to 0, x divided by, x is common in the denominator, 1 plus m. Now x and x gets cancelled, and so the limit when we apply, we have only m. So this will be equal to 1 by 1 plus m. That is, this is im. I have left that I over here. So please write that. So this is im, and therefore we have im over here. So it is 1 by 1 plus im. So which means that the limit, the value of the limit will depend on the value of m. So this implies, so the value of the limit depends on the value of m. So as m keeps on changing, the limit also keeps on changing, because when m is equal to 1, the limit will be 1 by 1 plus I. And when m is equal to 2, it will be 1 by 1 plus 2i. we see that the limit is not unique. So if the limit is not unique, it means that the limit does not exist at the origin, and therefore the function f of z is not continuous at the origin, since the first condition itself is not satisfied. I hope you would have understood this problem. This is one of the significant problem in the examination point of view. Thank you.